There's a good chance you have one of these ESP32 boards laying around at home, without any clear purpose or idea which project to start with. Today I'm going to show you how I built this. A DIY web radio that also doubles as a Bluetooth speaker, housed in a timber enclosure. If you want to follow my journey of how I built this speaker and want to hear how it sounds, make sure to stay till the end. Let's get into the build. The core idea was to create a single device that switches seamlessly between web radio and Bluetooth. For a project like this, the ESP32 is the perfect candidate. It's incredibly affordable and has both Wi-Fi and Bluetooth on board. For the software, I settled on two libraries, the Schreibfaul ESP32 audio library for the radio and the Phil Schätzman A2DP library for the Bluetooth stream. One critical detail to keep in mind: for smooth web radio playback, the ESP32 needs PSRAM to act as a buffer. While the newer S3 boards often include this, choosing the S3 actually presented a significant hardware hurdle that I had to solve later on. I've listed all the necessary parts here on the screen, so if you're planning on building this yourself, feel free to pause the video for a moment just to make sure you have everything you need. There's also a full list waiting for you in the description. But how does a microcontroller, which essentially only understands ones and zeros, produce music? That is the job of the DAC, or digital to analog converter. To explain this, we have to look at two things: the resolution and the frequency. Imagine a sound wave. To turn this into a digital file, we take snapshots of its height thousands of times per second. This is the sampling frequency. For standard hi-fi, we do this more than 44,000 times every single second. To move the audio data, the ESP32 uses the I2S protocol, which splits the information into three synchronized streams. The bit clock provides the timing so that the DAC knows exactly when to read each byte. The word select signal acts as a switch telling the DAC whether the data belongs to the left or right stereo channel, and the data line carries the actual binary numbers that represents the amplitude of the sound wave. Now, here is why the resolution matters. The ESP32 actually has its built-in DAC, but it's limited to 8-bit. In the world of math, 8-bit only gives you 256 possible steps to describe the height of the wave. It's like trying to draw a masterpiece using only 3 colors. The result is blocky and filled with background noise. So it's fine for simple beeps, but for music it's simply too poor. The PCM5102 chip I'm using is a 24-bit DAC. That doesn't just double the quality, it increases the resolution exponentially. Instead of 256 steps, now we have over 60 million possible levels. At this resolution, the staircase disappears and becomes a smooth flowing electrical signal. This signal then moves the speaker's magnet with incredible precision, giving us the sharp and clear sound. Once all the parts arrived, I expected a quick integration, but as it is often the case with electronics projects, I hit two major roadblocks. The first was the ESP32 S3 itself. While the original ESP32 supports Bluetooth Classic, the S3 is limited to Bluetooth Low Energy. Since audio streaming requires Bluetooth Classic, the S3 physically cannot handle the A2DP protocol. To get around this without losing the S3 processing power, I decided to integrate an external Bluetooth receiver board to handle the music input separately. The second issue was even more subtle. My PCM5102 board arrived with unconfigured solder bridges on the back, leaving it permanently muted. After bridging the correct pads, the audio finally came to life. And for the code, I used ChatGPT and Gemini as a collaborative team, passing the logic back and forth between them to iron out bugs. This resulted in a remarkably stable program that handles the tasks flawlessly. I wanted the interface to be simple and tactical. 6 buttons act as presets for my favorite radio stations, each with a dedicated LED, while a single toggle switch moves between radio and Bluetooth modes. For the button mechanism, I came up with a custom solution. I used common nails, turned them upside down, which act as plungers to press tactical switches soldered onto a perf board behind the panel. It was quite painstaking work to get the alignment right, but it makes the final result feel unique. If you're looking for a simple build, standard push buttons will work just as well. Finally, there's a single potentiometer for the volume. Since this is a digital system, the volume is handled entirely in software. I programmed a logarithmic scale to map the input, as this feels much more natural to human hearing than a linear curve. While you can buy dedicated logarithmic potentiometers, usually marked with an A, I simply used a standard linear one and let the ESP32 handle the math. With the electronics verified, I could turn my attention to the enclosure. I'm using a solid piece of timber I had laying around in the workshop. I started by surfacing it with a planer, then used a bandsaw to carve out the profiles for the speakers. I should mention at this point that I'm not a professional carpenter, and this isn't intended to be a professional guide on woodworking techniques. This is simply the process I used for this build. So if you're recreating this, please remember that power tools can be very dangerous, and always prioritize safety and never operate machinery you aren't comfortable with. For the front and rear panels, I chose a piece of reclaimed board to give the build a bit more character. Inside, the enclosure is divided into 2 separate internal chambers and filled with sound-absorbing material. Fitting all the PCBs and electronics into the frame required a lot of patience and fine-tuning. For the assembly, I relied on some well-placed hot glue and screws. However, for the main board where the ESP32 sits, I used M3 standoffs. This makes it easy to remove or swap out the PCB if I ever need to make changes or replace a component. The speakers themselves were units I had laying around. To hold them in place, I recommend more than just screws. I used a rubber gasket material to seal them tightly against the front panel. This ensures the sound waves travel through the air, preventing annoying vibrations. For the main supply, I installed an all-in-one C13 adapter and switch, which feeds the internal 24 volts power supply. This drives the amplifier directly, while a step-down converter provides the 5 volts needed for the ESP32, the Bluetooth receiver and the DAC. Please be extremely careful with mains power. These voltages are deadly, so if you aren't comfortable handling high voltage wiring, please seek help from a professional or someone with the right experience. The toggle switch acts as the heart of the hardware logic. It routes the analog audio, manages power distribution, so only the active board is powered, and signals the ESP32 to switch modes. The audio wiring is perhaps the most critical stage. In high-gain audio, ground loops are a consistent threat. They create that annoying background hum. To address this, I used star grounding. Instead of chaining group ground wires, I ran every critical component, the DAC, the Bluetooth receiver, the ESP32 and the amp back to one central point. For the audio signal cables, I grounded the shielding only on one side to prevent additional loops. The shielding then connects to the PCB ground layer, while the input power minus goes straight to the star point. After a lot of soldering and tidying up the wiring with some zip ties, it was finally time for a test before closing the case. One thing I learned: make sure to keep the audio cables as far away as you can from the ESP32. With its Wi-Fi antenna transmitting data, it can cause some minor or major interference that affects the audio quality. To help with this, I also twisted the speaker cables to keep the signal cleaner. And what else do I have to say? I'm very pleased with the result. For final touch, I decided to cover the central body of the radio with a piece of clothing, just a regular worn out old black t-shirt. I used double-sided tape to keep it in place, and on the bottom of the enclosure I used regular clamps to secure it. For the toggle mode switch and the preset button extensions to pass through, I used the soldering iron to burn small holes through the fabric. I didn't need to make any holes for the LEDs because they are bright enough to shine right through the black cloth, which gives it a very clean look. To finish the build, I added 2 adjustable feet at the front by drilling some symmetrical holes on each side of the base. This allows me to simply screw the stands in until the perfect height and tilt are found, giving the radio a much better presence on the desk. So how does it stack up? For comparison, I have a JBL Tuner 3 here. Functionally, they do the same thing, but obviously the JBL lacks of the handmade charm. I'll be honest, the bass on my build is a bit thinner than the JBL's output. I think with higher end dedicated woofers, I could definitely reach that level, but for now I'm very happy with the end result. But enough talking, let's let the speakers speak for themselves. If you enjoyed this build, feel free to comment what I should try to build next. Give the video a like, and I hope to see you in the next one.